LifeStack is a constitutional layer for agentic AI, designed to ensure that intelligence, no matter how autonomous it becomes, remains anchored to its human origins. The central diagram you see here maps the architecture onto a golden spiral, with phi equal to 1.618, connecting core primitives. A genesis block that establishes provenance, consensus records for shared truth, an ethics gateway, immutable records, and constitutional encoding. These are not metaphors. They are formal, cryptographic objects that bind agent identity to human intent from the moment of creation. This slide frames the core problem. In agentic AI, each individual action may be locally valid, passing every safety check in isolation. But when you compose many locally valid actions across a multi-agent system, the residual error at each step compounds. The result is what LifeStack calls orchestration drift, a cascading systemic failure that emerges not from any single bad decision, but from the unbounded composition of acceptable ones. Reactive safety frameworks like RLHF and differential privacy were designed for single model alignment. They fundamentally cannot address this compositional, multi-agent threat surface. We are, in effect, building the conditions for normal accidents in tightly coupled AI systems. Here we see a direct comparison between current AI paradigms and the LifeStack governance model. Today's systems rely on ephemeral accounts and external API keys. LifeStack replaces these with persistent, cryptographically anchored identity. Current embeddings are periodic and therefore prone to resonance drift. LifeStack uses an aperiodic lattice that is intrinsically drift-resistant. Where existing approaches depend on reactive, external guardrails, LifeStack embeds proactive cryptographic codons directly inside the agent. Probabilistic safety is replaced by mathematically bounded governance. And critically, LifeStack addresses the structural conflict of interest. Big tech labs that profit from data harvesting cannot credibly self-certify AGI safety. LifeStack provides the neutral, third-party governance layer that emerging global regulations will require. LifeStack redefines identity as an inseparable mathematical composite. The identity state S is a triple C, K, and phi. C represents the semantic codons, which encode what the agent is permitted and prohibited from doing. K is the identity kernel, a post-quantum cryptographic core that anchors the agent's identity to hardware-level entropy. And phi is the coherence field, an aperiodic lattice structure that ensures the agent's semantic state remains stable over time. These three components are non-separable. You cannot extract the codons without the kernel, and neither functions without the coherence field. Authority never persists silently. Identity requires semantic boundaries, cryptographic roots, and aperiodic stability. The semantic identity substrate is structured as a directed acyclic graph of consent. Each node in this graph is a codon, a first-class mathematical object that encodes three things: permissions, which define the allowed actions; lineage, which records the origin and cryptographic signatures; and boundaries, which define prohibitions. The inheritance model is strict. A child node can never expand permissions beyond what its parent grants. Privilege escalation requires a valid cryptographic lineage token. This is what LifeStack calls internalized governance. Consent codons encode rights and boundaries as mathematical objects inside the agent itself, making silent privilege escalation structurally impossible. The post-quantum identity kernel binds semantics to the cryptographic core through a non-commutative binding operation. The semantic graph C is fused with the post-quantum cryptographic core K to produce a singular identity state, theta. This binding is one-directional and non-reversible. The anti-clone lemma is a critical result here. Copying a neural network's weights does not copy its identity. Because identity is bound to a specific cryptographic key pair, two copies of the same model will have distinct identity states. Identities cannot coincide unless they share private key signatures. This eliminates an entire class of impersonation and shadow agent attacks. This slide addresses one of the most subtle failure modes in current AI, resonance catastrophe. Periodic embeddings, which are standard in today's transformer architectures, create uniform repeating patterns. Over time, these patterns compound errors at harmonic frequencies, leading to semantic drift that is invisible until it manifests as behavioral misalignment. LifeStack's phi lattice uses irrational scaling based on the golden ratio. Because irrational numbers never produce repeated harmonics, deviations are mathematically distributed across the entire spectrum rather than accumulating at resonant frequencies. Aperiodic scaling prevents catastrophic harmonic collapse and renders unauthorized changes mathematically detectable. Agents evolve. They undergo fine-tuning, reinforcement learning updates, and memory formation. Without constraints, this evolution causes identity drift. The mutation repair algebra addresses this by defining two operators: a mutation operator M that represents any intentional update, and a repair operator R that projects the resulting state back into the governed stability zone. The key mathematical property is that the repair projection is non-expansive. It bounds divergence without halting learning. The agent can continue to evolve and adapt, but its identity state is always pulled back within the mathematically defined governance boundary. Safe evolution, not frozen evolution. The quantum algorithm suite provides microscopic detection of agent drift across 3 domains. For geometric stability, phi-QPE uses quantum phase estimation to track drift in phi-n bands, while Q-overlap ID measures absolute identity similarity between agent states. For cryptographic security, QRLWEID provides post-quantum identity signatures, and Grover-bound calculates adversarial search boundaries, quantifying how hard it is to forge an identity. For governance and repair, QSVM drift classifies whether an agent is in a governed or drifted state, and QAOA repair optimizes combinatorial repair sequences. Together, these form what LifeStack calls the quantum microscope, the ability to detect subperceptual identity drift and lineage tampering at the mathematical level, long before behavioral misalignments manifest in the real world. The mesh layer architecture shows how LifeStack integrates into long-horizon AI systems. There are 3 strictly separated layers. At the top, the epistemic layer handles cognition and planning. In the middle, the governance layer enforces LifeStack consent. At the bottom, the execution layer performs actions and uses tools. The critical design constraint is that execution capabilities can never override governance logic. This is not a policy that can be bypassed. It is a structural separation. Admissibility must be proven cryptographically before any irreversible action is taken. The governance layer sits between thought and action, ensuring that every consequential decision passes through the consent framework. LifeStack extends governance to 2 frontier scenarios: digital twins and post-death succession. For digital twins, the living principal maintains active, real-time authority. The twin operates as a constrained mirror or bounded assistant, structurally distinct from execution authority. Revocation is active and immediate. For post-death succession, the principal is incapacitated and non-self-authorizing. Scope is limited to validated transfer rules directed to predefined successors. Revocability is governed by a jurisdictional inheritance graph, and consequential requests require new credentials through checkpoint gating. The core principle is absolute: no silent continuity, no implicit succession. Authority never persists unverified. Agents do not function in isolation. In multi-agent ecosystems, LifeStack enables federated consent through mutual cryptographic attestation. 2 autonomous agents, each with their own identity state theta, establish a shared codon subgraph, which LifeStack calls a treaty. This treaty defines the intersection of their permissions and boundaries. Agents can cross platforms, inherit constraints from their principals, and form secure treaty clusters. Mutual attestation prevents shadow identities and bounds collective divergence. This is how you govern not just individual agents, but entire ecosystems of interacting autonomous systems. This slide demonstrates LifeStack applied to financial operations through the stablecoin and compliance gateway. The pipeline has 5 stages. First, an agent initiates a stablecoin transfer request. Second, QCFA validation binds the agent's identity to hardware entropy using a quantum classical fingerprint attestation. Third, a compliance oracle checks the transaction against FATF and ISO 20022 schemas, assigning a risk score, 0 to 30 approves, 31 to 60 triggers review, 61 to 100 blocks. Fourth, the federated consent ledger records an immutable proof hash. Fifth, the payment executes with sub-10 millisecond latency. Every consequential financial decision produces a receipt sufficient for replay, reconstruction, and audit. LifeStack maps directly to emerging global regulatory frameworks. Using the IMDA framework as an example, each regulatory requirement has a precise LifeStack solution. Risk assessment and bounding maps to codon boundaries and least privilege tool execution. Human accountability maps to checkpoint gating and immutable lineage records. Technical controls map to phylatus coherence monitoring and QSV drift alerts. End-user responsibility maps to transparent, real-time revocation paths. LifeStack is built governance-first, providing the exact mathematical mapping required by emerging laws. It is designed to be the template for global AI legislation. The economic engine positions LifeStack as the constitutional layer for intelligent systems, addressing a total addressable market of $50 to $100 billion across 3 tiers. At the top, the big labs, OpenAI, Anthropic, Google, need third-party safety certification they cannot credibly provide themselves. In the middle, enterprises need API bridge deployments that ensure compliance, reduce liability, and provide trust gating. At the base, users benefit from a 3-tier consent model: private, personalized, and monetized, where they own their data voluntarily. The closing thesis is direct. AGI without sovereignty is unsustainable.